of the system into two parts to study entanglement, and so I'll mention some of these. There'll be some numerics, and then for the more theoretical part, I'll again be using the construction of some trial states from conformal blocks in conformal field theory, and then I will use some methods to do calculations here and derive a kind of effective field theory description for the entanglement spectrum. And again, this will use this generalized screening hypothesis and the idea of a conformal boundary condition. And finally, with some corrections to scaling, I can really study and rather well explain the entanglement spectra that we find numerically. Okay, so first we'll talk about bipartite entanglement. So the usual thing we want to do in topological phases is we take our system and we divide it into two parts in real space. We just divide it into two pieces. And there's, with local degrees of freedom, there's then in the full Hilbert space, not some low energy description, but the full Hilbert space, we imagine we can divide the Hilbert space into a tensor product of two pieces, A and B, and then, since we have that decomposition of Hilbert space, the ground state wave function is a sum of tensor products of pieces in part A and in part B. And there are some coefficients, and so this is the so-called Schmidt decomposition, or maybe more properly, it's equivalent to a singular value decomposition of a matrix. One can sort of think of this as a matrix and do the same decomposition. And when I write this decomposition, what is implicit is that the psi A ends and psi B ends are orthonormal basis states in the respective Hilbert spaces, so that these are orthonormalized, and then therefore there are coefficients e to the minus epsilon n over 2, which we can take to be real by choice of phases of these basis states. And the overall normalization is 1 over square root of z, where z is the sum of these e to the minus epsilons. Sometimes epsilon is replaced by psi on these slides. And so z looks like a partition function. The e to the minus epsilon n looks like a Boltzmann weight for something, and we'll be pursuing that relationship. So these epsilon n's, or sometimes psi's, could be called pseudo-energies. They look like energies, and the spectrum of these forms what we call the entanglement spectrum. The term comes from Lee and Haldane, actually. So this is one way to do the Schmidt decomposition. An alternative way is to say we take the outer product of the ground state with itself, and then we do the partial trace over part B of the system, trace over the degrees of freedom in HB, and we end up with a reduced density matrix for part A. So now we have a density matrix, not a quantum mechanical pure state, and in terms of the same decomposition, it's basically equivalent. Now we have this, and so this is a density matrix which is presented in diagonal form in this way. So the trace of rho is 1, and with a density matrix, we can do one more nice thing. We can define the von Neumann entropy of the density matrix as minus trace of rho log rho. So this is very standard. Probably most people know this. I don't know if anyone else in the school really discussed this. We can talk about it a little bit now. Okay, so these are most basic definitions. Now let's come to topological phases, and I'll now be focused on 2 dimensions only, 2 dimensions of space. Let's suppose that what we take for part A is at least topologically a disk. Doesn't have to be circular, but it's a disk. And the outside is part B. The remainder is part B. And let's say the circumference of my disk is L. So Kitaev and Preskill and Levin and Wen, at simultaneous times in 2006, argued that as the length of the circumference goes to infinity, the entanglement entropy has the following universal form. First, there's a non-universal coefficient times the length of the boundary. So this is what people call an area law, although here it's a length. and the subleading term of order 1 minus gamma, well, gamma is called the topological entanglement entropy. And this is supposed to be a universal or topological property of a topological phase. So this is the topological part, hence the name. And furthermore, they showed that gamma is the log of this curly d, which is sometimes called the global quantum dimension. And this is related to things which I haven't really said much about, the quantum dimensions, square root of the sum of the squares of the quantum dimensions, or alternatively, 1 over the 0, 0 entry of the modular S matrix, which has shown up in various talks. So this is a finite matrix indexed by the quasi-particle types, the set of quasi-particle types, and 0 is the trivial object. Okay. So there are various questions we can ask. I'm not going to review the derivation of this result, which is a bit off my topic, but there are various questions we can ask about what has to go in order to see this kind of result. So one question is, how exactly are we supposed to define this partition? So this is an issue that we'll discuss. What are the necessary and sufficient conditions to get this result? And so on. And furthermore, well, in more detail, we could think about the entanglement spectrum. As Haldane likes to emphasize, the entanglement spectrum in the reduced density matrix may or does contain, at least in the low energy, low pseudo-energy part, contains more information than just the entanglement entropy. And we'll be seeing that this is something, there's something universal about that spectrum. So how do we understand this topological entanglement entropy from the entanglement spectrum? Okay, so let's look at the entanglement spectrum in more depth. Now, the Kitaev and Preskill paper, towards the end, there's a passage which I think has often been overlooked, so I'm reproducing it here. So here's the actual text from the paper. This is what they said. Well, first they say we can think of the marginal density matrix. We already know that. And now then they said, now we make a natural but non-trivial assumption that H, this is an operator or beta H, the eigenvalues of beta H are the pseudo-energies I was talking about. So H can be regarded as the Hamiltonian of a 1 plus 1 dimensional conformal field theory, blah, blah, blah. But the entropy associated with this conformal field theory should then correctly reproduce the universal constant term. And so what they have in mind here, in context in the paper, they seem to have in mind fractional quantum Hall states, actually, at this point, where we have this chiral theory on an edge, and they seem to have in mind that this CFT is the same as in the edge theory. And when we have a chiral CFT, we have some known results that I'm not going to review that tell us that by a modular transformation argument that basically lead us to the form of the entropy that I had on the last slide. Okay. So if you make the assumption that the spectrum is something chiral, and like a CFT, and here's the plot of what I mean versus an angular momentum quantum number, basically a momentum along the cut. This is the sort of way the spectrum will look later in the paper. So if this is a CFT, this is just everything on a straight line. You have because it's chiral, you just have a direct relation between energy and linear momentum. And so what they're saying is that if the spectrum has this form and it's a CFT, then it's easy to understand this result for the topological entanglement entropy. Okay, so in the later paper of Lee and Haldane, they studied explicitly the entanglement spectrum using orbital partition, which I'll describe in a minute, and they focused mainly on the multiplicities of the eigenvalues of the pseudo-energies. They found that there's a low-lying part and some higher energy part. They focused mostly on the multiplicities of the low-lying part below some gap, and found that these seem to agree with, at least if we go to the thermodynamic limit, the multiplicities in the spectrum agree with what you get in a real edge, in the edge states of the quantum Hall effect. Okay. So this is slightly different, you see, from what Kitaev and Preskill were saying, because they really had in mind the eigenvalues as well as the multiplicities of the eigenvalues. And so arguments for these kinds of conjectures were advanced in various later papers. Some of them are really in the form of the Kitaev-Preskill idea, and some are just more restricted to multiplicities, as in Lee and Haldane. And some of these authors considered only free fermions, some considered trial quantum Hall states, and some people advanced general arguments for the whole thing, which are fine, basically. And what I'm going to describe is an alternative line of argument based directly on trial quantum Hall wave functions. All right. So now I'm going to describe how to look at entanglement in topological phases or in quantum Hall states specifically. So there's the two ways which are called orbital and particle partitions were put forward quite early on. Notation, I'll use n sub a for the number of particles in part A, which is a good quantum number. N sub b is the remaining number of particles. The angular momentum of, so rotation, I'll always have some rotation symmetry, so the angular momentum of the particles in part A is LZA. And now here's how I'm going to define the partition in this orbital approach. So let's look at the lowest Landau level and put it on a cylinder this time with circumference L. And in this case, it's convenient to use the Landau gauge. We have explicit translation symmetry along the y direction going around the cylinder, so we can use plane waves in the y direction, and then we find that in the x direction we just get a Gaussian centered at the value of ky, just at ky, in my units where the magnetic length is 1. So that means that each eigenfunction that I get, these are for the lowest Landau level, each eigenfunction in the lowest Landau level is centered as a Gaussian near this point. My skills with PowerPoint aren't good enough to put a little Gaussian here, but it's sort of localized near this point, but it's spread around the circumference and it's a plane wave. And so as I increase ky, this shifts along the cylinder. And because of the periodic boundary condition, ky is an integer m times 2 pi over L. So I have a discrete set of states. And you see, so position in the x direction is equal to y, ky. So if I restrict to looking at states with ky less than some constant I can choose, that's very much like looking at x less than ky. So that basically means if I take ky here, I'm looking at states to the left by restricting, just looking at ky less than this constant. Now that's not quite accurate because there's a little fuzziness here, there's a little smearing because of the Gaussian. It's not a precise relationship, it's a bit of a rough relationship. But the idea is that this is like dividing the system into two parts in real space. So that's orbital partition. To do the case of the sphere, I basically just cap off the cylinder at the ends to make a sphere. I can take it to be a precise sphere and not an elongated one. In this case, quantization on the sphere, we get very much the same thing, except that m takes values between minus n phi over 2 and plus n phi over 2. And actually, the conventions are that m could be either integer or half integer, depending on whether n phi is odd or even. And then what you can take would be, for example, you take part A to be consist of the orbitals in m positive, with m positive, and the remainder is m negative, probably flipping the sign compared with what I did here. In this case, the LZA, the angular momentum, is just the sum of the mi's, basically in both cases. Okay. Then there's also particle partition, which I may not even get to use at the end of this talk, but roughly the idea is that we just divide the particles themselves into two groups. Let's break the permutation symmetry and say, okay, these particles are one type and the others are another type, and you just look at entanglement between them. And so at least at the outset, this doesn't even involve dividing the real space into two parts. It just involves partitioning the particles themselves. Okay. So now, following Lee and Haldane, we'll look at orbital partition. Here are some, they're not actually their results, but from some other papers that I used, but it's the same form. And so what they found, plotted versus LZ, it turns out that because of the way we've set it up, the pseudo-energies tend to increase from going from right to left. So that's the way it's plotted. And here is the gap between this low-lying branch you see, which is sort of chiral, everything's going in one direction, then there's a gap, and then there's other messy stuff up here which does not really look chiral. It's more like massive excitations in a sense. And furthermore, this is for nu as a half, you have similar results for nu as a third. They found that when you use the Laughlin trial state at 1/3, you get this low-lying part and nothing up here. The other stuff has gone up to infinity and disappeared. Because infinity means the weight, e to the minus epsilon or psi here, is 0, so they just disappear from the Schmidt decomposition. So here there's a direct comparison between the result for the trial state and the result for a realistic ground state, as was used here for Coulomb interaction. The low-lying part in the same size is remarkably similar in the two cases, but this one has this extra sort of junk up here. Okay, so this is probably non-universal stuff, whereas there probably seems to be something universal going on with this low-lying branch.
All those are orbital partition, right?
This is orbital partition, yes. Okay. Now, of course, there are finite size effects. These are sort of finite size truncated spectra, but at least at the low-lying levels, the multiplicities, if you count in the vertical direction in the low branch, these agree with the edge theory, the states on the edge of the same Laughlin droplet at low sizes. And presumably, if we increase the system size, all of the multiplicities here converge to those that you would have in the edge theory of the infinite size system. Yes?
This seems to say that there's a universal preferred edge theory, contradicting the idea that anything with the right anomalies is on the same footing.
Indeed. However, that may be because I've rather specifically focused in on a particular trial state where we do know the edge theory. So there may be a rather boring answer to that question.
Nick, can I just, since I have a paper on this?
Yep.
It's perfectly possible to be in the same quantum Hall phase, and much as the physical edge can reconstruct, the entanglement spectrum can reconstruct by other branches coming down. So Ed is absolutely right. It's
Right, okay, thank you. That's a better answer. Did everyone hear that answer?
No, why don't you repeat?
The answer is you could have edge reconstruction. The way that works is that some of what I was calling junk up here, which would be non-chiral stuff, these are the many particle states, so you get a sort of continuum. Well, you could have something here that's like a massive mode. It comes down and it mixes with this, and some other things then become gapped and lift off again, and you end up with a different edge theory.
So these
With a
would only
different set of modes going maybe right and
So
left.
the so-called universal stuff would only be sort of quasi-universal.
Only quasi-universal, yeah. Thanks for clarifying. Okay. So, yeah, all right. So I guess what I'm describing in this talk is going to be theory for spectra like this in the Laughlin, or in the trial states, and I'm basically ignoring this point, actually, so I don't want to overstate things unintentionally, so what I'm describing is perhaps more quasi-universal than fully universal. All right, but even with this, there's something here to understand. And in practice, so I mean, you can raise this issue, but in practice, with the realistic state, what you see is this kind of perhaps the minimal spectrum that you can have that does agree with the trial state. Okay, so now let me make a couple of observations about orbital partition. First, if I apply this to the filled Landau level, lowest Landau level, the orbital partition is basically trivial. The reason is that in this case, we have a slated determinant. All the states in the lowest Landau level are filled. So when we cut the system into two parts, what we get is simply a product of two slated determinants, one for each part. There's one term in the Schmidt decomposition, And so if I'm foolish enough to make a plot of the entanglement spectrum, there's only one level in the spectrum. So this is very certainly not the same as what you get on the edge of the nu is 1 state, which is at the least a chiral Dirac fermion, and I guess would be maybe more complicated if you reconstructed it. What you certainly can't do on the edge is reduce it to something with no gapless excitations. So in a sense, if you take at least the way that this seems to be stated in the Lee-Haldane paper, originally, the idea does not actually apply in orbital partition to the case of nu equals 1. All right. And now another observation. This orbital partition, although I explain why it's roughly something like cutting the system in space, it's not actually local in real space. And the idea for this is very straightforward. I deliberately avoided, when I was talking about it, emphasizing too much the fact that what we're doing is really cutting in momentum space. If we look at the y direction, we are explicitly making the cut in momentum space between ky less than something and ky bigger than something. And you know what happens if you have something which is discontinuous in Fourier space and you transform it back to real space, you get some long-range dependence. And so what happens So that's an exact statement for this particular case. Now, if we take this, we can figure out how to express this in terms of we write the field operator in terms of those single particle eigenstates, and then we can explicitly restrict to what we want to restrict to, so that if we take correlations that are restricted to live in part A, that's ky negative, now we have this cut in Fourier space, and the correlation function has a long-range tail going along the cut in the thermodynamic limit here. It decays exponentially as you go away from the cut. Here the cut is at basically x is 0, and this decays as a Gaussian if you go into the left side of the system, but more importantly, along the cut, it decays with a power. So this illustrates that this orbital partition is not really local in real space, even though it looks approximately so. Whereas the Kitaev-Preskill arguments assume that the cut really is local. So this may be a problem with the use of the orbital partition. And indeed, one thing about the orbital partition was that the spectrum that we saw, to be honest, looks a little messy at low energies. It doesn't sort of fall onto a nice straight line, and it has some odd features. For example, there are some degeneracies. Let me just go back for a second to this. I think in examples here, you can see that these two levels appear to be degenerate, or here. Some of these levels seem to be degenerate, and at least in some cases of these, I know that these are true exact degeneracies, and they're due to some symmetries that are left in the system. This is calculated on the sphere. There are certain symmetries that account for these degeneracies. But these would not occur if it was the conformal field theory type of spectrum. All right. And sometimes the spectra look even a little bit more strange than this. They sort of start here and come down a little and go up again.
Can I just comment?
I finally provoked Duncan.
Since you're commenting on this stuff,
Yep.
the orbital entanglement cut is, we've separated the Hilbert space into the non-trivial part of the quantum geometry and the trivial part.
Okay.
Of course, put them back together.
Yeah, all right. Well, that's the alternative point of view. I will pursue my point of view. My point of view is that we shouldn't really go to the lowest lambda level in this problem. Okay, all right. So here's the point. All right, so. Okay, that's a good question. So if I have an edge, I mean the ground state of a chiral edge theory, then of course in that case I do have long-range correlations. But what happens when we're looking at entanglement is we are looking at correlations in the bulk of the system. If you make let's say you make a cut locally in real space. Well, if I look at correlations of inside part A, they should be exactly the same as if I hadn't made the cut. That's the whole point. You see, you can trace out part B. We're looking at things in part A, so I can trace out part B. It literally makes no difference. So these should not have those things. So it's a very good point. I don't know if I have something relevant on the slides here. Let me just go back and remind you that what we actually get way back in the here, if we look at the reduced density matrix for part A, this is not the ground state of this thing, which I'm saying may be like the edge theory. This is a finite temperature state. And when you have a non-zero temperature, even in the gapless edge theory, it produces a correlation length, and correlations decay exponentially. And so that's, because we have that kind of structure here, that's why this will be able to reproduce, as we'll see eventually, to reproduce the real space correlations, which decay exponentially. Okay. All right, so now there's a third way that we can do a partition on the quantum Hall problem. We can take the view, perhaps different from Duncan's, that even if I'm talking about lowest Landau level states, they live in the full Hilbert space that includes all Landau levels. There's nothing to stop me from saying that I partition my real space, my coordinate space, into two regions just using the original xy variables. And that means in terms of wave functions that if I want to trace out part B, I'm going to be taking some wave function times its conjugate, and I just integrate over, the coordinates are going to be put equal, and I integrate over region B. Just integrate them out. So that will give a reduced density matrix. Now a couple of generalities. For a system of n particles, the way that we often do a partition of a system of particles is we start by partitioning the single particle space into subspaces. So this is just what we were also doing in the orbital case. So then for the single particle space, we have a direct sum decomposition of it into two parts, not a product. But then when I look at many particle states, what I get, if I restrict to n particles, what I get is a Hilbert space with NA particles in part A, NB particles in part B, and I have a direct sum of these over all NA and NB that add up to n. Okay? So this then looks much more like the kind of partition that I was talking about. One further thing is one should be very careful in practice if you have fermions and not bosons, because there are minus signs involved in the decomposition. Because of fermion operators coming through here and hitting here, it's really a graded tensor product. And this is closely related to what Greg Moore was describing as the Kojal sign rule the other day. Okay. So now if we apply this kind of thing to the problem with a magnetic field, when I just cut in real space, I have my maybe Gaussian wave functions in the lowest Landau level, I just cut them. What I'm left with is not in any reasonable sense in the lowest Landau level. I just cut the function into two parts. When I'm thinking about entanglement, there's no particular reason to be worried by that, because when we take a ground state and we partition it to look at entanglement, we're not trying to do this in some low energy subspace. We just do it to the whole state. And finally, of course, the real space partition is manifestly local. All right, so this was actually studied in some free fermion problems a bit earlier. And so what happens if we go back to the case of the cylinder, for simplicity, if I make a cut somewhere at x0, my basis states are basically Gaussians in x, centered at my ky. So I cut them into two parts. If I integrate the part of it that lies in part B, what I get is an error function. right? Because I integrate a Gaussian down to some limit that's not plus or minus infinity. If I use the sphere, it turns out I get incomplete beta functions. Never mind. Okay, so basically each single particle wave function gets split into two pieces. One has weight in part A, one has weight in part B. These squares of these weights have to add up to 1. Let me call them alpha and beta and get rid of the phases. So I can define those weights. And then what I find if I take the case of the filled Landau level is that since it's a single particle problem, free particle, non-interacting particle problem, not surprisingly, the spectrum that I get is itself described in a free particle manner. The total pseudo-energies are just sums of single particle pseudo-energies times the occupation number for each of these states m, where epsilon m is given by a formula in terms of alpha and beta, the weight in the two parts. Very easy and very nice exercise to derive this, which I think is in pretty much any of these references. Okay. And so we have a free fermion spectrum, and what I sometimes call the cut ground state, the lowest pseudo-energy state, or in other words, the state with the biggest weight in the decomposition, is the state in which these negative the negative pseudo-energy states are all occupied, the others are unoccupied, and then the excited states are particle hole excitations on that ground state. I'll show you a little more in a second. The orbital partition can be thought of as doing exactly the same thing, except that the weights alpha and beta are 0 or 1, depending on whether m is on the left side or the right side. And so by doing this, what we've done is we've removed this sharp jump in momentum space and smoothed it out, and that's why it gets rid of those artifacts. So if we make a plot for this single particle pseudo-energy, it's just a curve like this. It looks like a chiral. Look near the middle. It manifestly looks like a chiral fermion spectrum. So the Fermi energy is up somewhere here, and we fill up everything below 0, and then the higher excited ones involve making particle hole excitations across. It's also important to realize that in this decomposition, the particle number in part A is not fixed to be anything in particular. There are sectors with different values of n sub A. All right, so here are the many particle entanglement or pseudo-energies plotted for a fairly large system. And so in the low energy part, you see you get something that's very straight on the lower edge, but it does fan out as you go up in energy. Down here, it looks like they're all falling on a straight line, as you would have in a real conformal field theory. And furthermore, if you plot them, the spectra versus NA, the lower edge is parabolic, which is also what you expect in the conformal field theory, if you like, of a free Dirac fermion. Okay. All right, so that's a free particle calculation. So now we'll come to our trial state. So here are some generalities. So if the partition is defined locally in real space, correlations in part A are just those of the full system, as I mentioned before. So these are short-range correlations. And so now let's look at this reduced density matrix. We can call this H the entanglement Hamiltonian. So what we would expect generally, so I'm going to try to apply effective field theory ideas to the entanglement spectrum. And because I'm insisting on real space partition and using the word locally a lot, what I expect is that, well, while I may have some d-1 space-dimensional theory on my cut, some Hilbert space of this form, my entanglement Hamiltonian should be local. It should be a short-range Hamiltonian. It should be constructed out of local operators. It's an integral along the cut of local operators on the cut. In some field theory, which may be a chiral theory, that's okay. And one argument why this should be the case is that if I look, because I have short-range correlations, even if I'm close to the cut, if I look at regions of space separated by more than a correlation length, they're approximately independent from each other. So therefore, if you like, think classically for a second, classical analog. If I look at the statistical weight, the probabilities associated with different regions, and I go along the cut, regions that are further apart should be statistically independent. So therefore, the probabilities should factorize as a product, which means if I write it as an exponential, it's like the exponential of a sum. In other words, it's like the exponential of a sum of local terms. So this is a bit hand-waving, but this is motivation for why this entanglement Hamiltonian should be, in a sense, a short range, should consist of short range or local operators in whatever theory it is, provided I'm maintaining locality when I do the cut. There's no formal proof of this, but we'll see that it appears to be working. Okay. All right. Okay, first I've restated here what I just said, basically. Now I want to come to trial quantum Hall states, and now we would expect, following the earlier authors, that the one-dimensional theory I want to use is just the chiral CFT of the edge theory. Now, I guess when we did this, we were a little naive. We didn't think about the reconstruction kind of idea, so it's not so totally universal. But this is the expectation, maybe somewhat naive. Okay. So then, if we look at the spectrum, we would expect this conformal field theory spectrum, which if I'm plotting these total energies now, I don't have a single particle picture. This total spectrum itself is just linear because it's a chiral theory. And there's some velocity, if you like, here, which is, dimensionless in our units. Okay, so one point here is that the orbital spectrum, the orbital partition spectrum, cannot reduce to this form even in large size. If we take the view that we can resolve the discreteness between the levels, it cannot take this form even at large size unless the velocity is zero. And that's because there are these exact degeneracies in the spectrum. There's no way for those things to all become non-degenerate in the thermodynamic limit. The only way to have that compatible with this is if the slope is zero in the limit. Whether that takes place, I don't know. Okay, so here's a spectrum derived numerically from this real space partition procedure for the nu is a half Laughlin state. You see again, it's rather like the nu is one spectrum I showed you. It looks pretty low-lying part of it. It's pretty straight at the bottom. There's a little bit of curvature. There are more levels. It fans out. In fact, it's rather like the nu is one spectrum. Here's another one. This is for nu is a third. It's plotted sort of on a different vertical scale. You can see more structure here. It fans out. There are some characteristic things that seem to stick out here. Here's the low-lying part, which looks like quite a nice spectrum, but again, there's some fanning out. This was all done for a particular value of Na, which is exactly a 1/2 the number of particles, and the lowest pseudo-energy for each number of particles, these again pretty much fall in a parabola, like in the nu is one case. Okay. So all of those are features that you would expect if you take the chiral edge theory with a single scalar field, chiral scalar field on the edge. So now I'm going to switch a bit, and I'm going to talk about trying to explain and calculate these features using trial wave functions and conformal field theory ideas. Okay, so first, we've seen all this already. We make the trial wave functions as correlators. The way I'm going to handle the background today is to get charge neutrality is I'll put an out state here, not the vacuum, but something with charge n. And here I've written an explicit curly r. In an operator point of view, these products of operators are radially ordered. In conformal field theory, we sometimes think in the Hamiltonian language in which the radial variable is the time. We have a Hilbert space on a circle. As we advance the radial variable, we move outwards, make the circle larger. And then that's the Hilbert space point of view for calculating the correlation functions. Okay, and so my A is the same as before. Oops. So now, using that Hilbert space point of view, I can take my trial state I just wrote down, and what I can do on a circle of radius r, there I have a Hilbert space in CFT. I can use the completeness relation in that infinite dimensional Hilbert space, and I can write 1 is equal to an outer product of basis states, which I have to sum over all the basis states, and there's different values of the charge quantum number there, depending on NA, which is how many particles appear inside that radius, because everything's radially ordered. So the relevant number of relevant charge to put in these states here, I could put all the charges here, but the relevant number is the same as the number of operators that happen to be sitting at positions inside the circle. And if I had taken the radius to be 1, I could drop these factors. L0 is the part of the Virasoro algebra. It's the Hamiltonian for evolving outwards in radius. So that's the completeness relation. If I plug that into my previous correlation function, then I get two separate expectations multiplied together and summed over NA and K. I say I am summing over NA here. And I can think of each of those as wave functions. So then I get something that's very nearly the Schmidt decomposition. I've decomposed my wave function into a sum of products of two pieces. Let me explain my notation quickly. Since I have two kinds of Hilbert space here, the single angle brackets correspond to states or expectations in the conformal field theory Hilbert space. I'm now using double angle brackets for states or wave functions in the physical 2+1 Hilbert space. So in terms of the states, these are functions that I obtained by putting this into the correlator, and I have a sum over these products. However, I don't know about normalization of these at this stage, so this is not quite the Schmidt decomposition. It's just some set of functions that are indexed the same way as they were in the conformal field theory. So what are these wave functions? Well, they look just like the ones that I had for n particles. I've got the vacuum here, I've got NA of these operators, and then on the left, it's more general than what I had before. I have not just the vacuum or the charge NA vacuum, but I have some general state indexed by K in that sector of the conformal field theory. And so it turns out that, although I'm not going to show this here, that if I make this more general construction of trial functions using general out states of the conformal field theory, what I get are exactly the edge states, the trial functions for the edge states of a system of NA particles. And as NA goes to infinity, these become linearly independent, and the space of these edge state trial functions is in one-to-one correspondence with the states in the conformal field theory. It's a very beautiful correspondence. I remind you that the theory for the edge, especially for the Laughlin state, was worked out by Wen in about 92 or so, or 1990. So the first comment about this decomposition is that this immediately predicts that the multiplicities, as studied by Lee and Haldane, as NA goes to infinity, the multiplicities in the decomposition are those of the conformal field theory on the edge. Well, unless, of course, some of these turn out to have norm 0. But assuming that, then this gives their result for the multiplicities. Although they were doing orbital partition, we're doing real space partition. If these are orthonormal, then we've actually got the Schmidt decomposition. So what we really need to do now is we need to study the matrices of inner products among these. We need to understand the inner products. Okay. First, though, I have an example in real space where I can do this decomposition without even using conformal field theory. So here I take the Laughlin state, and let me use symbol Z for particles that are inside radius r, and W for the particles outside radius r. Not quasi-holes, these are particles, but just to distinguish which and which, I'll call them Z and W. So then the Laughlin state falls into, the product turns into three parts, ZZ, WW, WZ. And now I'm going to look at this WZ part that connects the two. This is where the entanglement comes from. I can extract all the powers of WLs that I can, and then exponentiate what's left and write it as exponential q and then log of 1 minus z over w. That's just an identity. The whole thing is identities, in fact. Then, since mod z is always less than w, I'm allowed to expand the log in powers. I get this expansion, and then I can expand the exponential in powers as well. And now look what I've got. I've got a Laughlin state for the z's and a Laughlin state for the w's, and then I've got a whole bunch of things which involve z times w, which give the entanglement. And these are already written in terms of powers. I can take the sum over particles inside the sum over n and write it in terms of products of these combinations j, a minus m and jb minus m, each of which are the sums of powers of coordinates. So this is some symmetric polynomial expression, and in fact, so each term in this big sum that I have here is some function of z's times some function of w's. And these functions of z's are written as these sums of powers multiplied into the Laughlin function. Well, these sums of powers are exactly one way to write the edge excitations of the Laughlin state. And so J is the coordinate, this is the coordinate representation of the current operator, the raising modes of the current operator acting on the Laughlin state. So these are exactly what appears in Wen's description of the trial functions for edge states of the Laughlin state. Also, I think Duncan did that. Okay, so these are not all, there's an infinite sum here. These are not all linearly independent for finite size, but when NA and NB goes to infinity, these do become linearly independent, and so we get the full set of edge states here, although we still don't know about the normalization. So this is beautiful. This is, these are identities that are well known in the theory of symmetric polynomials, actually. Well, you could say that, but then I am saying that some of them are in A and some of them are in B. So in some sense, when I do these particle systems and I want to partition it into two parts, you may say that I'm always in some way breaking the permutation symmetry to do that. But that's just how it is. We have to do that to look at entanglement. There's nothing suspicious about it. Yes?
But we're not considering a fluctuation of the number of particles in A or in B.
We are considering it because there are terms in this sum. Oh no, I'm sorry, yes, you're right. So what we've done here is we've looked at a piece of the wave function which has a particular value of NA inside the radius, but of course there are other pieces with different numbers.
Okay.
Okay, so now the overlap integrals. This is a more difficult problem. For the Laughlin state, we can relate this whole thing. So what we really want here, in view of what I just told you, if I'm doing the Laughlin state, what I really want are basically just the norms or the inner products between trial states for the edge excitations. And in fact, in one of Wen's papers, he uses the screening in the plasma to derive the inner products, the form of the inner products to leading order, and shows that the inner products between these edge states are exactly, in some sense, exactly what you get in the conformal field theory. Have exactly the same form, up to some overall constant. It's a very beautiful result. So I'm not going to do that special case here. I'm going to give you our argument about the general case of our conformal field theory construction and use generalized screening. And his results are a special case. So here's the sort of thing we want to calculate. I've now dropped the A on the N here just to simplify notation. And so I need to calculate these norm squares by integrating over ZI's. And on the left, I have some general state in the CFT with the same N as in the number of operator insertions there. And so this is, as I was discussing yesterday, like looking at a perturbed conformal field theory, perturbed by some operator, written slightly different way here. So the effect of the background that's needed when I do the integrals, I definitely need the Gaussian factors, otherwise maybe I don't care about them. the effect of that is that these particles are living inside the disk-shaped region. Okay. And that also because of the fact that we did the real space partition. And again, I'm going to use the generalized screening property. Connected correlations of local operators in the perturbed conformal field theory decay exponentially, as they do in the plasma. Now, these out states, what are they? Well, all of the out states can be obtained from the out vacuum by acting with A daggers on the vacuum. So these are the same operator as A, but I'm using the adjoint field here. So these, remember that A generates the chiral algebra. A and A dagger generate the chiral algebra of the CFT that we get from our construction. And so if I want charge n, it's, actually this may be a slight, I may have misstated this slightly, but roughly speaking, we can just act with A daggers to the left on this vacuum and get all of the states in the CFT. We might actually need to use more A daggers and also some A's, but the net charge of the operator has to be n. And so this, and then what one does to get these K's is we need to take modes of these by integrating, doing contour integrals and taking linear combinations. Okay. So now what we can look at instead of these things indexed by K is we could look at things where we have a bunch of A daggers in the correlator, and maybe some additional A's actually. It wouldn't make any difference to the arguments. So we have some A's, and in the left moving part, A bars under the conjugate here, which are integrated over. This Zi is the same as this Zi. And we have some other operators, A's, A daggers, and A dagger bars. And these can be at different positions because we have to take the mode expansion for the function and the conjugate separately. So this is rather like looking at the norms of quasi-hole states, except instead of quasi-hole operators, we have A daggers, and instead of, and also the W's are not equal to the W primes. Okay, so now for these, the A dagger here, for example, is not entirely local with respect to the operators A bar A. A bar A picks up a minus sign to some power when you go around the A dagger. Another way to say this is that the A dagger of W, although the A bar A, which appears in constructing the plasma, just has electric charge, A dagger, or A itself, contain electric and magnetic charge, or in other words, vorticity. They act like a vortex. So they try to make the phase of A bar A wind as you go round, and the consequence is that these don't just disappear into the plasma, but correlations of them decay exponentially with distance if you put them in the plasma. So if I take one of these coordinates W and actually bring it inside the disk, which I'm allowed to do as a mathematical discussion at least, then this amplitude is going to decay exponentially with the distance of W from the boundary. It's like there's a branch cut from W to the boundary of the disk. Okay. So these are, in a statistical sense, they're excluded from the disk. They don't really want to live inside there. And so this screening has a certain effect that as A dagger approaches the boundary of the disk, it becomes equivalent to an A bar also at the boundary of the disk. So here's another way to think about that. So A dagger is creating some excitation. It's an operator. Let's think of it as creating some wave, okay? It's field theory after all. And we know from the previous discussion just now that this wave can't propagate into the plasma. It decays exponentially. So what happens if you have a wave impinging on a boundary beyond which it can't propagate? Anybody? Faculty members?
It gets reflected somehow.
Thank you. It gets reflected and it comes back. And what that means, since it went in as a right mover, in a Lorentz signature picture maybe, it comes back as a left mover. And in the Euclidean signature, if it goes in as a W, a right mover, chiral field, it comes back as an anti-chiral field, function of W bar. Now then there's a question, does it come back so it's an A-bar or an A-bar dagger, but which one is it? So you have to look a little bit carefully at the charge quantum numbers to see that what happens is that it comes back as without the dagger. So there's an effective boundary condition. A dagger of W on the boundary is, at least up to some phase, the same as A bar on the boundary. Okay. So this is, at least that's the leading order effect at long distances. So this is an example of a conformal boundary condition. Strictly, to be as simple as I've written it here, I should conformally map the exterior of the disk region to the right half plane. I can do that because it's still conformal out there. And then it takes this simple form at the boundary on the imaginary axis. Okay. And this corresponds closely to the arguments that Xiaogang used in his old paper, in which he was using screening arguments and image charge methods in electrostatics to make the arguments in the Laughlin plasma. So when we have, what it now means is that although we have right moving and left moving fields, we have a non-chiral CFT in the exterior region. They're connected by this boundary condition on the boundary. So, and especially if I think of this as the right half plane, I can unfold that and get a copy of the whole plane, and now I have a chiral theory, but in the full plane, instead of a non-chiral theory in a half plane with a boundary condition. It's the same thing. It's a very common trick. Okay? And because this is a conformal boundary condition, it preserves conformal invariance, this actually works. And so the result is now that when we do this and we go back into our calculation, we realize that this basically means that it's equivalent to doing the integral over the particle coordinates. That's what we wanted to do. It means that the A dagger here and the A dagger bar here sort of gets reflected, and they become the conjugate fields to each other in the unfolded theory. And so we can conclude that at least for large size, the inner product of two of these, going back to the basis state labels, two of these basis states is just equal, up to a constant that doesn't depend on k and k prime, is equal to the inner product of those things in the CFT. So if these are orthonormal, then these are also orthonormal. It's quite amazing to me that one can actually make such a statement. And this agrees, of course, with Wen's results for the edge case, for the Laughlin case. So we did some checks on this on moderately good sizes using Monte Carlo, and it works quite well. Okay. So for our purposes, we need a little bit more than what I just said. We need corrections to scaling. And the reason is that if I just take what I just said, if I just go back a couple of slides here, if I can find it. If I take what I just said, that would mean that these basis states here in the decomposition are already orthogonal. And you see what that means is that apart from the normalization question, it means that all the pseudo energies must be equal. It means my spectrum is totally flat. And since I'm not really quite happy with that answer, not quite satisfied, I want more, I need to look at corrections. So there are going to be corrections to scaling. If I look at shorter distances, that conformal boundary condition story is not quite exact. So the consequence is that there's a line, when I unfold, I've got this line still, but I've got some operators sitting on the line. I've got some perturbation of my conformal field theory sitting on the line. And in the expectation, I can write this as e to the minus s, again with an integral of local terms in s. And what are these operators? They're operators in the non-chiral CFT, and they should be local on the line. They have some coefficients that I can't possibly calculate. So they should be local, and they should be U1 neutral operators, just for obvious symmetry reasons. And so there's many such possible operators. They could be descendants in the CFT and all kinds of things. They're built out of A and A dagger, basically. And by scaling arguments, the coefficient is related, slow down. The coefficient is some lambda alpha, which by scaling has the form of some length scale A to the H alpha minus 1, where A is an ultraviolet cutoff, or we can think of it as being the particle spacing in our state. So there is a length scale built in. So what's allowed to appear here? Well, in general, we have a U1 symmetry, so there's a current operator. We could have a J0 there with the coefficient mu, like chemical potential. We could have the stress tensor of our theory, such as the U1 part, and we could have other descendant operators. If all I have is the stress tensor term here, then with this perturbation, L0 is diagonal if I use the right basis here. That gives me exactly the linear spectrum that I was hoping to get earlier. Okay? And the mu J0 term, although it's perfectly allowed, sometimes it's absent for symmetry reasons. Its only effect is to shift the value of the charge Na in the ground state. So that's a rather uninteresting effect. And so the dominant effect of interest at large distances, you can think of it as little a goes to 0, is the one with the smallest power, which is the stress tensor term, or L0 or Hamiltonian term, which gives the linear spectrum. So this is a rather typical effective field theory argument, including the way that the coefficients are supposed to behave. And this implies that if this is true, this implies that as we go to larger sizes for our cut, the spectrum is going to collapse onto the linear spectrum. Okay. So to do better with the fit, we'll take the stress tensor and we'll take the two operators which are of next leading order in the CFT, which are things like d squared phi all squared in scalar field language. And we can numerically find the spectrum with those terms added to the Hamiltonian, and we can compare with our numerical calculation. So what we did is we made a fit. Since we have three unknown coefficients, we made a kind of chi-squared fit to get a best fit to some bunch of eigenvalues in the spectrum. So the red ones are the real spectrum. The blue ones are from the operator I just said, and if you can see this, you see that there's a fairly good correspondence, and in particular the structure with these branches that appear here and go in, appear here, go in, and so on, is quite well reproduced. These things only go up to a certain level, and then they, finite size, they stop appearing. In the in the field theory analysis, that truncation isn't really seen because it's an infinite size. But a lot of the low-lying spectrum can be well reproduced with this picture. So we believe we understand what's in this low-lying spectrum, and we believe that we understand that it really does approach in the thermodynamic limit the behavior of the CFT, and not only in multiplicities, and not only does it collapse onto a linear spectrum, but we even understand the corrections to that scaling picture. This is all done for the Laughlin state, I should have said. If we do the Moore-Reed state, we expect to have two different velocities because there are two decoupled stressed energy tensors that we can use, and that should appear in the spectrum, although we haven't done a detailed study. Okay, so I have some minutes left. I might say a word or two about particle partition, or I could basically wrap up. But since we have like 20 minutes left, I think maybe I'll say a few more words about this. But this is just like an addendum. This is not very essential. What I've already told you about is the main part of the story. But I can actually do some analysis also for particle partition. And it is kind of cute. So here's how I more formally define particle partition, our way of doing it. One way to think of this is that we're going to first take our system of spinless particles, and we're now going to add to the system an additional pseudo-spin degree of freedom, and instead of up and down, I will suggestively call the components A and B. So those are the two spin components. And so to introduce those degrees of freedom into my state where they don't exist, I'll simply multiply my let's say totally symmetric state. I'll just multiply that by, I guess I'm mixing wave function notation and Hilbert space notation. But I have my state psi, which is equivalent to this wave function, and I'm multiplying that by the spin state. which is just independent of everything about the z's, and it's just an unentangled state with A plus B for each particle. So that really does nothing. Since this is totally symmetric under permutations of particles, it does not change the symmetry of my whole function. So if this is symmetric, this is also symmetric. So this is really doing nothing, done absolutely nothing here. But now what I do is I decide to look at the entanglement between the upspins and the downspins, the A and the B. And you may say from this, well, that must be trivial. But it's not trivial in general. Okay. And in the language I used earlier, this is equivalent to setting alpha m equals beta m equals 1 over square root 2 for all m, regardless. And you can easily see that from this. So in this case, we certainly have all Na in the spectrum, unlike the way that people defined particle partition originally. And we have to sum over Na when we take the trace. And now one feature of this is that when we do this on the sphere, for example, which has rotation symmetry, this spectrum will also exhibit full rotation symmetry. Nothing we did violated rotation symmetry in space, not spin space, but space. And there will be, because of the SU2 or SO3 rotation symmetry of the sphere, there will be degeneracies in the spectrum because of that symmetry. And one further point is for a filled Landau level, it's always nice to do these free fermion examples early on. If we do this, it's quite easy to see that all the pseudo-energies in the particle partition are equal. We get a trivial spectrum. Not trivial in multiplicity, but trivial in eigenvalues. Here's an example of what you get from a Laughlin state for 1/3, and I've color-coded the different particle numbers. It's a little hard to see, but it's a very strange-looking spectrum. If we start from the maximum possible L, and here I'm plotting it versus total L, so each of these levels is a 2L plus 1 multiplet, okay, because of rotation symmetry. Anyway, it does look rather different because here's sort of the top of the spectrum. The maximum LZ occurs in this multiplet here, but some of these things have lower pseudo-energies than this one, and other things are going up. And at 0 and 12, we get only a single level. 1, we get some other things. Here we have just a single band of states. We can understand those features. Not very interesting. But what about the other structure here? So the thing is to focus on the region up here near the maximum L's. That's the L of part A. So if the particles making part A have very large angular momentum, that means they're mostly near the North Pole. And so in this region, we're now back to the picture where if we put them as close as we can, with the largest LZ we can, or largest L we can, this is like the ground state, the Laughlin state. And the excitations, which have smaller values of L, are going to be like edge states. And so this region actually corresponds to this sort of picture where the entanglement spectrum involves a decomposition using edge states like we had before. If we go too far from this region, then I don't really know what happens. Okay, and so then there's some analysis for this. I'm not sure if I want to go through all of the analysis. There are various remarks. For example, the rotation, in this case, rotation invariance for the Laughlin state, the U1, the stress tensor of the U1 theory is actually not allowed to appear in the pseudo-Hamiltonian because of rotation invariance. So that means, and that, remember, that was what gave us the characteristic linear spectrum. So rotation invariance says that's now absent. So that linear, the slope of that thing becomes 0. And everything is controlled by the subleading terms. Well, here's a subleading term we can put in, and here's a bit of sort of semi-classical analysis for that, which I don't really feel like going through right now. But it does explain some of the features. Maybe I should. So if we look at the spectrum, first if I plot it just for one value of Na, as I did before, and if I also plot it versus Lz, not versus total L, then my multiplets become these sets of levels that are now separated. So I have degeneracy like this. And if you sort of look at this picture and tilt it, see this becomes a straight line. And here are these bands that come out, stick out from the sides of my fan. So that apart from an overall tilt, this is actually rather like the spectrum I had before, really quite similar. And so the point is that the same kind of fitting using subleading operators can explain these features. And for example, the pattern of these largest ones in these bands are quite easily understood in terms of some details using these operators. And likewise for NA, it turns out that the same leading correction term that I'm using, in this case there's only one allowed by symmetry, gives us an inverted parabola for the psi min, and unlike the other case. And so basically, this is just plotting in a different way the same spectrum that I showed you before here. These ones, which start here and go down, this corresponds to that inverted parabola because L is like LZ squared, I guess, right? I think that's the reason for that. So that's basically the inverted parameter in the other plot. Oh, I'm sorry, it's because that's plotted versus NA. And I think if you look at this, somehow if you look at this long enough, you realize that this is equivalent to the inverted parabola on the other figure. Right now I forget exactly why that is, but never mind. Okay, and so we can explain a lot of the features of this spectrum in that part of the spectrum, which is rather closely related to edge states. All right, so that's basically it. So if we use real space partition and also part of the particle partition spectrum, we can understand the locality of the pseudo-Hamiltonian. We can do a lot of the calculations that are needed, and it agrees nicely with this Kitaev-Preskill picture. Bonus information we understand inner products between edge states. So we have some results about particle and real space partitions where we have analytical understanding. We don't have any comparable understanding, as far as I know, no one has it, for the orbital partition spectrum, which involves something non-local along the cut. And the main features, and even this kind of idea of using a scaling analysis and an effective action or effective Hamiltonian using local operators and scaling, applies not only for trial states, but for the spectrum in the more general case. I think that's all I want to say. Thanks for your attention through these lectures. Thank you.